Hello everyone. Already we have studied 5 modules in fiber optics and networks. So let us revise from the module 1 what we have studied in module 1. Module 1 is about the introduction to the optical fiber communication. So you know what are the different types of communication system, like how to transfer the information from one end to another end, either wired or wireless line. So here wireless means the information can be transmitted through the radio frequency, or it can be transmitted through the microwave frequency, or copper cable can be used to transfer the information. In this optical fiber communication is done through the optical fibers. So here transmitter and receiver are transferring the information through the channel is called it as optical fiber. So optical fiber made up of glass material. And what is the need of going for the optical fiber communication? So yeah, you already know what is electromagnetic spectrum. What are the different frequency ranges for radio frequency, microwave, infrared, far infrared, and for optical fiber communication, the communication is done in the range 10 raised to 13 to 10 raised to 16 hertz. So that is the frequency reserved for the optical fiber communication, or it is a visible light spectrum that itself is used for the optical fiber communication. You can see here the frequency is very high compared to all other frequency or all other communication system. Radio frequency, it is around 10 raised to 4 to 10 raised to 6 hertz. Microwave 10 raised to above 10 raised to 9 or 10 raised to 10 hertz. But here it is around 10 raised to 13 to 10 raised to 16 hertz. As you increase the frequency, what will happen? The carrier frequency is high, then the bandwidth, obviously the bandwidth required or bandwidth utilized for the communication, optical fiber communication is very high. So that's why, because of this uh, range, because of this carrier frequency, the bandwidth of the usage of the bandwidth for the optical fiber communication is very high, so that more information can be transmitted through these optical fibers. That is the main advantage of the optical fiber communication. So today the technology has been developed to provide data transfer speeds of 1 petabit per second. So because of that main the bandwidth or transmission capacity, it has increased to 1 petabit per second. So that is the need for the optical. So what is optical fiber? Optical fiber is a flexible transparent fiber made up of high quality glass material or silica, or sometimes plastic also used for making optical fiber. Here it is widely used in fiber optic communication, so it will be used for transmitting the data over a longer distance and with a higher bandwidth. And because of this fiber, there are many application advantages that we'll study later. So this is the one of the question appeared in the last year question paper June 2019. With the help of neat diagram, explain the main blocks of an optical fiber communication link. So what to write for this question? So optical fiber communication link or system consists of source of information, electrical transmit, optical source, optical fiber cable, and at the receiver end photo detector, electrical stage and destination. So what is this? Already you know what is the communication system. General communication system should consist of one is optical transmitter end, receiver, and between the transmitter and receiver channel will be there. But here in the optical fiber communication, transmitter and receiver should be there, but the channel is itself is the optical fiber cable. So here the source of information, it may be in the analog signal or a digital signal, but here the main thing what we need to include in the transmitter and receiver, like whatever the information transmitting through the optical fiber is in the form of light signal. So whatever the electrical signal or information should be converted into optical signal before transmitting through the optical fiber. So transmitter should consist of one converter, electrical to optical converter. So that will be done by optical source. Optical source which converts electrical signal into optical signal or electrical signal into light signal. After that, that information will be transmitted through the optical fiber in the form of light signal, and at the receiver end, because for the further processing and at the destination receiver end, it should be received as electrical signal. So after transmitting through the optical fiber, it should be converted back into electrical signal. So that process or that operation will be done by photodetector. Photodetector, it receives the light signal information in the form of light signal, and it will convert the light signal into electrical signal, and that will be transmitted uh, further in the receiver side, and it will reach at the destination. So this is the optical fiber communication system. So optical source will be, we will going to study in the module 3. Different types already have studied. LED and laser as optical source, which converts electrical signal into optical signal, and photodetectors, pin photodiode and avalanche photodetector. These two photodetector converts the light energy into electrical signal. And optical fiber act as a channel. Through optical fiber, according to the total internal reflection ray theory model, the light will transmit it to the optical fiber. This is a concept, or this is the communication system in the optical fiber communication that you need to write for that question. This is the digital optical fiber link using laser diode and avalanche photodetector. So if the digital information, original information in the form of digital signal, then it should be encoded. After that, it should be given to the laser drive circuit, and that laser converts the electrical signal in the digital form into light signal on off keying. Like wherever 1 appears, it will on the light, wherever 0 appears, it will off the light. So that output from the laser will transmit it to the optical fiber cable. Then it will be received at the photodetector, at the avalanche photodetector, that converts the light signal into electrical signal. Then amplifying the signal by amplifier and equalizer. It will remove all the noises, like whatever the noise beyond the bandwidth. So it acts as a low pass filter. Whatever the signal beyond the bandwidth, that will be removed, and that will be decoded and received at the receiver side. This is the overall digital optical fiber link using the laser diode and avalanche photodetector. Because of this fiber, there are many application advantages that we'll study later. And attenuation is lower than coaxial cable because of the optical fibers and the principle of transmitting the data with the total internal reflection concept. There is no much loss in optical fiber, and also because it is made up of plastic or polymer or glass material, insulating material, the interference is very less, and the resistance, there is no the power drop or heat dissipation in the fiber takes place. If you compare the copper, it has some resistance. Because of the resistance, what will happen? Some voltage drop takes place, power dissipation takes place as heat, but here there is no much attenuation. That's why it can be used for a longer distance without any repeaters. So attenuation is very low compared to the coaxial cable or twisted fiber, and does not radiate energy, so that the signal security also more, and not necessity any equipment for protecting against grounding, voltage problems like that. So because of the fiber optic network operate at high speeds up to into gigabits, can be it can be used for a higher distance, and because of the more bandwidth, it will provide more information, more data can be transmitted, so that the data bit rate, number of bits per second, is more in the optical fibers. Low transmission loss, it is around 0.2 dB per kilometer, and also it is made up of very thin hair size glass fibers, so that weight as well as size is very small compared to the coaxial cable or copper. So it can be placed easily in the ships, aircraft for transmitting the data. So very low, small size and low weight. So this is one of the question appeared in the last year question paper. Explain the advantages, disadvantages and applications of optical fiber communication. So you need to explain what are the advantages, what are the disadvantages, what are the applications of optical. Advantages already explained: broad bandwidth because of the high frequency, electrical insulator because it is made up of silica glass, so there is no electricity, non-conductor of electricity, immunity to electromagnetic interference because electrically non-conductive, so it does not act as a it is immunity to attenuation loss over longer distance. It is around low attenuation 0.2 dB per kilometer in optical fiber cables, and the lack of costly metal, so small size, weight, ruggedness and flexibility, system reliability and ease of maintenance, and also high security. There is no much loss in the information in the optical fiber, so it provides high security to the. So what are the disadvantages of optical fiber communication? So here the thing is, the skilled manpower is required for the optical fiber communication to install the optical fibers, and also there is a higher initial cost during the installation, and it will be expensive over a short distance. Only point-to-point working is possible, and the precise and costly instruments. Jointing of fiber and splicing also time consuming. Adding additional node is also difficult. More is expensive to repair and maintain. And it requires the skilled and specialized manpower, and specialized and sophisticated tools are required for installing, repairing, everything in the optical fiber communication. These are the disadvantages. So these are the uses where it can be used in communication, fiber optic sensors, illumination, medical, and it is mainly used in telecommunication industry. This optical fiber mainly used. What are the applications? It is especially advantageous for long distance communication because light propagates through the fiber with a little attenuation compared to electrical cables, and this allows long distances to be spanned with few repeaters. So it will be used as a sensor to measure strain, temperature, pressure and other parameter, and also it will be optically used as a hydrophones for sonar applications, and few applications like in medical, military, electronics, and it will be used in one of the main advantage in the medical field as a endoscope, keyhole surgery. So optical fiber can be used in the endoscope. So these are the applications of the optical fibers. So you need to write the advantages, disadvantages and application of the optical fiber communication for that. Yeah. So what are the different, how it will be transmitting fiber to fiber to home, for providing the network, providing the network facility to the node or to the home, it can be used FT2N, FTN or FTH fiber to home. So if you see the optical fiber, what are the different layers? So innermost layer is core. Then the cover, core is covered with another material. It is made up of a glass with a refractive index is lower than the refractive index of the core. That part is called as a cladding. Then different coating part, strengthening the fiber, cable jacket. These are the different layers in the optical fibers. So it is like this: core with a it is like depending on the different fiber, it may be a single fiber, single mode fiber or multimode fiber. Single mode fiber with a core diameter is very less. For multimode fiber, core diameter is around 550 to 100 micrometer. In the cladding, it will be just, it is more than the core diameter. Then buffer and jacket, it provides the mechanical strength to the optical fiber. So this already very, what are different parts. So what is a refraction? A refraction, look, what is the light propagating principle within the optical fiber? Like uh, you know what is light refraction, reflection. If you consider the two medium with a different refractive index, if you incident the light between the interface between the two medium, how it passes through that medium, whether it reflects, whether it refracts, that we need to. So refraction is the changing direction of the light when it goes into a material of different density. With a two medium with a different density, how it going to reflect and reflect? You can see in the diagram incident rate. It is shown in the red color. Some part of the ray, it reflected back to the same medium, other will refracted into the other medium. So if you consider the two medium, one is air and another is water, if the incident ray incident to the interface between the two medium, some part of the ray reflected, other part will refracted. So depending on the what angle of incidence and what is the angle of reflection, angle of incidence, and that should be considered. So here the refractive index, because we want to, what is the refractive, because the refractive index should be considered properly so that total internal reflection should take place within the optical fiber. So refractive index of the medium is defined as the ratio of the velocity of light in a vacuum to the velocity of light in the medium. So n. So the always for the to get total internal reflection, the refractive index of the core, because whatever the light, it should be incident into the core of the optical fiber. So it should travel within it should be confined within the core of the optical fiber, so that core of the refractive index of the core always should be greater than the refractive index of the cladding. So what will happen if you consider the two material with a different refractive index? According to the Snell's law, angle of incidence should be very important. So according to the Snell's law, n1 sin phi 1 is equal to n2 sin phi 2. n1 is the refractive index of one medium and phi 1 is the angle of incidence. n2 is the angle of refractive index of the other medium, and phi 2 is the angle of refraction. What is the refraction angle? So what will happen when the phi 1 increases, phi 2 approaches pi by 2. So this phi 1 is critical angle of incidence. So we need to consider what is angle of incidence. If you for a particular angle of incidence, the refracted ray just it will traces the interface, the interface between the two medium. Then the angle of refraction is pi by 2, 90 degree. That angle of incidence is called as a critical angle. If we increase the phi 1 more than that critical angle, then what will happen? The refraction ray will get completely reflected in the same medium. So that is the condition when phi 1 is not equal to phi c, what will happen? Less than phi c, that ray will get refracted. When phi 1 equal to phi c, critical angle, the refracted ray just traces the interface between the two medium, or pi by 2. And if phi 1 greater than phi c, the complete all that ray will completely, it will get total internal reflection. So that angle phi 1 greater than phi c, what will happen? Sin phi c is equal to n21 n1. That is by using the Snell's law. So that condition is used for getting the numerical aperture of the optical fiber. So one question it has asked in the last year question paper 2008, derive the expression for numerical aperture using ray theory. So what is the numerical aperture? Numerical aperture means what is the light collecting capacity of the optical fiber, that is defined by the numerical aperture. What is the light collecting capacity? What should be the angle of incidence to the optical fiber? Should be phi 1 angle of incidence should be greater than the critical angle, and at that angle of incidence, the whatever the light transmitted within the core will get completely, it will get total internal reflection, so that it will completely confined within the optical fiber core. So that is required, and for that internal angle of incidence, what is the numerical aperture of the optical fiber? So numerical aperture, what is the light gathering capacity or light collecting capacity? So derive the expression for numerical aperture using the theory model. That you have the equation for the numerical aperture. After the derivation, we will be getting numerical aperture is equal to n0 sin theta a, or n1 square minus n2 square to the power 1 by 2, square root of n1 square minus n2 square. That is the equation for the numerical aperture. Already we have given the derivation for numerical aperture using ray theory. It has been asked for 7 marks. You need to draw the diagram. What is the angle of incidence? This diagram you need to draw. Angle of incidence from the air to core phi 1, and what should be the phi 2, that is the angle of refraction. Then at the interface, core and cladding interface, what is phi? Angle of incidence to the core and cladding interface. That phi should be greater than critical angle phi c. Then it will get completely total internal reflection. There is no refraction. Then numerical aperture equation is this one. So it can be written in terms of relative refractive index difference, n1 square root of 2 into delta. Numerical aperture is in terms of n1 square root of 2 into delta. This we have the. So here the refractive index, because we want what is the refractive, because the refractive index should be considered for the numerical asked in the previous paper. With the need diagram, discuss the structure of single mode and multi-mode step index fiber with advantages for each type. So what is step index? So optical fiber mainly classified into two types, step index fiber and graded index fiber. What do you mean step index fiber? Step index fiber, the index, that there is a changes in the refractive difference between the what are paper is curve path, like at the center, refractive index is maximum, then gradually decreases towards the cladding part. So what will happen here, uh, like multimode graded images exhibit far less intermodal dispersion. Like we'll study this dispersion in the next chapter. Like dispersion, there is a pulse broadening takes place because of the different group velocity within the optical fiber. So if you see the single mode fiber, there is no changes in the um, there is no changes in the group velocity because of the single mode appears. Uh, but in the multi-mode, because of the different modes, there are different group velocities. So whichever the ray passes through the center of the optical fiber has the length is very small, like it will passes through the center of the fiber with the less distance, but because of the high refractive index at the center in the graded index fiber, the velocity is less. But if you go towards the cladding, the refractive index is very less, but the speed, the length also increases, but speed decreases, so that it will compensate speed and length in the graded index fiber, so that all the modes uh, passes through the graded index fiber reaches at the same time at the receiver end. But in the case of step index fiber, what will happen? Like entire within the core uniform refractive index, so that whichever the ray passes through the center, it will reaches first, and whichever the ray passes near the cladding, which reaches after the center ray. So there is a group velocity takes place, and pulse broadening or pulse spreading takes place within the optical fiber. That's why dispersion is more in the case of step index fiber, and it is less in the case of multi-mode fiber. So this is about the different types of multi-mode and step index, single mode, step index fiber, and graded index fiber. These are the classification of the optical fiber. You need to write for that question. Weight, ruggedness and flexibility, system reliability and ease of maintenance, and also high security. There's a difference between the different design parameters we need to consider for the single mode fiber. One of the parameter, like one of the design parameter, we should have the small core diameter. It's around 8 to 10 micrometer, and it is requiring very high precision at the connection as the use of laser source. And more thing, here the normalization for the numerical aperture means something. What is the it is like the V number. V number means it allows only single mode, LP01 mode. So what should be the V number or normalized frequency for allowing one single mode within the single mode fiber? It is around V is equal to 2.405. This should be less than 2.405. That is a normalized frequency or V number that allows only fundamental mode within the optical fiber. That's one of the design parameter. While designing the single mode fiber, V number must be less than 2.405. One more thing, normalized frequency and cutoff wavelength. The cutoff wavelength is the number of guided modes of the waveguide, depends on the optical wavelength. The shorter the wavelength, the more modes can be guided. For long wavelength, there may be only a single guided mode. So that's why for optical fiber, if it acts as a single mode fiber, it should be operated with a longer wavelength. That wavelength is called as a cutoff wavelength. So cutoff wavelength above which the particular fiber behaves as a single mode fiber. Normalized frequency is the frequency or V number. Below that V number, the particular fiber acts as a single mode. So V should be less than 2.405, but the cutoff wavelength is the wavelength above which the particular fiber behaves as a single mode fiber. So what are the different mode field diameter means actual diameter and mode field diameters are different. So always mode field diameter is greater than the actual core diameter. Like core, actually what is the requirement of the optical fiber? All light rays should be confined within the optical fiber. But practically this is not the case. So whatever the core diameter and the optical signal, if it travels within the core of the fiber, it will not completely confined within the fiber, just it will propagate towards the cladding part, so that actual diameter is, or mode field diameter is always greater than the actual core diameter. That is the mode field diameter. So the portion of the light travels in the cladding. So these things we need to consider while designing the single mode fiber. Single mode fiber, it allows only one mode, but how to design the fiber as a single mode? The normalized frequency must be less than 2.405. Cutoff, the wavelength must be greater than the cutoff wavelength, and mode field diameter should be considered for the single mode fiber. These concept we need to explain for the single mode fiber. What are the different design approaches? Okay, so thank you. In the next class, we will discuss about the module 2 old question paper questions. Thank you.